Hi everyone, welcome back to my channel. I'm Abhishek Paudel. Today I have taken a derivation from hydraulics, unsteady flow in pipeline chapter. So this is the derivation from continuity equation for unsteady flow in pipe. Okay, so let's get into the derivation. Let's start the derivation from the beginning. Okay, for this I'm going to take a control volume inside a pipeline. Let's draw a pipeline here. The pipeline is this one. And inside the pipeline I'm going to take a control volume. Let's say this is a pipeline here, so I'm going to take a control volume inside this pipeline. So let's take the control volume inside the pipeline. Let's take a section. This is a section 1 and section 2. So we have got a section here 1 and 2, and in this section the mass flow rate is how much? The mass flow rate is mass rate. What is mass rate? Mass rate means mass by time. Mass means volume into density by time. Volume by time means discharge. That is going to be rho q. Okay, the mass rate m dot is also called rho q. Mass rate m dot is also called rho q. Okay, so you have to understand that mass rate is also density into discharge. So by using the continuity you can say that rho into area into velocity. So because the continuity says that q is equal to area into velocity, this is how the mass rate is also can be also called as the product of density and cross sectional area and the average velocity. Okay, so this is the mass flow rate entering into the pipeline. In its section 1 is rho AV. Let's say this is rho AV. The mass rate rho AV is entering, and mass flow rate leaving is how much? Mass flow rate leaving is rho AV plus del rho AV by del x into dx. This is the mass flow rate leaving from this section number 2. Okay, this is the binomial expression. So you can say like the mass flow rate entering and mass flow rate leaving, you can write like this as a control volume inside a control volume, and expressing this as a binomial expression. Okay, using the binomial expression. So this is a control volume for continuity equation. Control volume for continuity equation. This figure is for continuity equation derivation. Continuity equation derivation. So let's get into the derivation. Okay, so let's consider the fluid element having length dx. Okay, this length is dx. Okay, so we have named this as a dx, and cross sectional area A and velocity of flow, which is the average velocity E B V, average velocity of flow B. Okay, from continuity equation you can say that inflow minus outflow is equal to rate of change of mass. Okay, rate of change of mass. You can say that inflow minus outflow must be equal to rate of change of mass by following the continuity. Okay, so what is inflow? Inflow here is rho AV. Here you can see inflow is the rho AV, and the outflow is the rho AV plus del rho AV by del x into dx. And how can we calculate the rate of change of mass? Okay, you can say that this is the equation number 1. Let's substitute all the values over here to get the expression. So let's get the rate of change of mass. Okay, so how can we get the rate of change of mass? That means rate of change of mass means mass is equal to volume into density. volume is equal to area into dx. Okay, the volume is cross sectional area A into dx is going to be volume. That is meaning going to be rearranging this rho A dx is the mass. You can see that this is the mass. And rate of change of mass is what? Rate of change of mass is, you can write like rate of change of mass. Rate of change of mass. Change of mass you can write like is equal to del m by del t. You can write like this. And del m is del rho A dx by del t. You can write like this. Okay. So this is the rate of change of mass. Let's substitute inflow here. Rho AV. Rho AV is the inflow. And outflow is the rho AV plus del rho AV by del x into dx is the outflow. And the substitute over here inflow, outflow, in rate of change of mass to get an expression. Okay. So now let's go to substitute this over here. So what is inflow? That is inflow is inflow minus outflow. Inflow minus outflow is gonna be rate of change of mass. Rate of change of mass. Inflow is how much? Rho AV. Outflow is how much? You know, rho AV plus del rho AV by del x into dx. This is the outflow is equal to rate of change of mass is del rho A dx by del t. This is the rate of change of mass. So let's put this minus. Let's cancel out this rho AB minus rho AB minus del rho AB by del x into dx is equal to, let's separate this dx here, del rho A by dx by del t. So you can cut this out. Finally you have got del rho A B by del x into dx is equal to del rho A by del t into dx. You can cancel out the dx also. So if you cancel out the ds, so you are gonna get, and rearranging this minus over here, we are gonna get like this del rho A by del t plus del rho A B by del x is equal to 0. It's going to be like this. We can convert partial differentiation, partial derivative to full derivative, because this is one dimensional flow. Okay, full derivative. So let's convert this. Let's write this like this: d rho A by dt plus d rho AB. D rho AB means change in mass flow rate. That is change in mass flow rate. D rho AB means change in mass flow rate by dx is equal to 0. Okay, now let's put the product over here. du dot v. You can do like rho dA by dt plus a d rho by dt is plus, you know, you can put the rho A outside, rho A dB by dx, because it is not dependent with respect to x, so that's why you can get the rho A outside 0. But here rho is dependent upon the time also, so the non-steady flow, so that's why you cannot just get it out. There must be the relationship. There must be the in unsteady flow, the density depends upon with respect to time, and the cross-sectional area also depends with respect to time. Okay, here divide by rho A now. Now divide. You have to remember to divide by rho A here. Rho A. You are gonna get like 1 by A dA by dt. 1 by A dA by dt plus 1 by rho d rho by dt plus dB by dx is equal to 0. So this is gonna be, the first term is gonna be elasticity, okay, and second term is compressibility. compressibility. Second term is compressibility. Okay, so now let's get this. We have got this as equation number 2. Equation number 2, because we have got the equation number 1 is the continuity equation. The equation number 1, inflow minus outflow rate of change of mass, and we have termed this as equation number 2, that is 1 by A dA by dt is the elasticity, and 1 by rho dV by dt is also the compressibility, and dV by dx is the expression change in velocity with respect to the distance. So that's why let's get this term, first term, second term, and substitute over here in the equation number 2 to get the final expression. Okay, now let's take the first term, that is 1 by A dA by dt is our first term. From where we need to start? Okay, we need to start from the area of cross section. Okay, so we know that the area of cross section is your pi r square, because you can see like in this is the radius r. The radius r is given. We can put this r. Please substitute this as a r is a variable, the radius of the pipeline. So pi r square is the area of the cross section. Okay, so now differentiating this with respect to time, because this unsteady flow which depends upon the time flow property, and the symmetric properties depends upon the time. So that's why dA by dt is equal to pi r square dr square by dt, dr square by dr into dr by dt. This is the chain rule. You have to apply the chain rule here, dr by dt. So gonna be like, dA by dt is gonna be like dr square by dr means 2r, 2 pi r. Okay, you have got 2r here, 2r. dr square by dr means 2r into dr by dt. Okay, into dr by dt. If you do like dA by dt is equal to 2 pi r square. If you do pi r square here, you have to divide it by r. 1 by r dr by dt. Okay. If you do pi r square over here, you have to divide it by r. So you can replace this pi r square by area. So dA by dt is equal to 2a by r into dr by dt. Okay. So if you divide it by, if you multiply it by 1 by a, multiply it by 1 by a, you are gonna get like 1 by a dA by dt, 1 by a dA by dt is equal to, if you multiply it by 1 by a, they are going to be 2 by r dr by dt, 2 by r dr by dt. You can substitute this dr by dt. As you know that change in radius by original radius means strain, dE. We can say this is a strain. So if you substitute this by strain, that is 1 by a dA by dt is equal to 2 dE by dt, 2 dE by dt. Okay, and now using strength of material concept, that is whoop stress, you can say this as a local equation number A. Using whoop stress concept, that strain is equal to stress by modulus of elasticity. Okay, the modulus of elasticity is equal to stress by strain. Okay, so as we know that sigma is equal to whoop stress, that is PD by 2T, PD by 2T. Okay, we have termed this as a PD by 2T, and let's substitute over here, that is strain E is equal to PD by 2TE, PD by 2TE. Okay, let's differentiate with respect to time t, that is dE by dt is equal to d by 2TE. You can get it out, d by 2T, that is dP by dt. Okay, let's substitute this dE by dt over here in equation number A. Here in equation number A, let's substitute this dE by dt over here to get the first term, that is 1 by A dA by dt. So we have to substitute this dE by dt, change in strain with respect to time, to this equation number A. Okay, now let's substitute this 1 by A, the first term, dA by dt is gonna be like 2 into 2 into d by 2te dp by dt. Finally, we are gonna get 1 by A dA by dt is gonna be 2 cancel out, d by 2e, d by te dp by dt. This is our first term. Okay, this is our first term. So we have got the first term here, and let's term this as the equation, local equation number B. Okay, we have got the first term in terms of this pressure, with change in pressure with respect to change in time. Okay, again now let's go to find out second term. Second term is what? The second term is 1 by rho. Here the second term is, so you can say that the second term is 1 by rho d rho by dt. Okay, you can say the second term is 1 by rho d rho by dt. So you can write like 1 by rho d rho by dt. How can we get this? 1 by rho d rho by dt. We use the concept of bulk modulus here. Bulk modulus K is equal to, we know that bulk modulus K is equal to, change in pressure by dp by d rho by rho. Okay, you can say this. We can convert this change in pressure by volumetric strain, and the volumetric strain is going to be same like change in density by original density. That means you can convert this one. So you can get the d rho by rho is equal to dp by k. You can substitute this d rho by rho over here in this above equation. We are going to get like 1 by rho d rho by dt is going to be d rho by rho. The d rho by rho is going to be dp by k dt. Okay, 1 by k dp by dt. This is going to be like 1 by k dp by dt. You can write like the pressure depends upon the time, change with respect to time. So we have got 1 by rho d rho by dt in terms of 1 by k dp by dt. Let's substitute this in equation number. Let's substitute this value. You can say that this value 1 by rho d rho by dt, this is the second term, is going to be like 1 by k dp by dt. You can say this as a local equation number C. So let's substitute this second term. This is the second term. Let's substitute this first term. We have got this first term over here, 1 by a dA by dt, and this second term, that is 1 by rho d rho by dt. Substitute in this equation number 1, which is the major equation. We have got equation number 2, which is the major equation in this equation. Let's substitute this in this equation. Okay, so what are we gonna get? We are going to get the expression is, let's substitute this over here in equation number 2. The equation number 2 is 1 by a dA by dt. This is the first term. We have got this plus 1 by rho d rho by dt plus dB by dx is equal to 0. Let's substitute this 1 by a dA by dt. Okay, the 1 by a dA by dt is what? First term, that we can write like d by te dp by dt, plus the second term is what? The second term is 1 by k dp by dt plus dB by dx is equal to 0. Okay, so now let's put this common from here, 1 by k dp by dt common. If you put this common, then what will you get here? Dp by dt is common, that is dk by te plus 1, dk by t plus 1 plus dB by dx is equal to 0. So you can say that this 1 plus dk by t, this 1 plus, you can say that this c square is equal to, you can say that k by rho 1 plus dk by t. This is the thickness t. Okay, this is not the time, this is the thickness. Here we can say this tm is tm, but in this case I have written here t. So understand, this is the thickness of the pipeline. So this is the celerity, and in case of short enclosure of ball bearing, pipe is elastic. Okay, so you can say that 1 plus dk by te is equal to k by rho c square. K by rho c square. So you can substitute this in above, substitute this above. Okay, substitute above, you are gonna get 1 by k dp by dt into k by rho c square plus dv by dx is equal to 0. Okay, so now then you can, this k cancel out, 1 by rho dp by rho c square, dp by c square dt plus dv by dx is equal to 0. Multiply it by c square, multiply by c square, we are gonna get 1 by rho dp by dt plus c square dv by dx. The c square is the celerity. Okay, this expression is equal to 0. This is the final expression we need this, and this is the continuity equation in case of unsteady flow in the pipeline. This is the expression for continuity equation. Okay, we have finalized the derivation continuity equation in case of unsteady flow in the pipeline. Unsteady flow in the pipeline. Okay, so I have done the derivation. Okay, I hope you understand up to this point. So let's meet in another video. So thank you so much for watching this video till the end. Okay, see you in the next video. Thank you.